Hi, this is Fadi, Session Lead for AWS Machine Learning Engineer Nanodegree. In this video, I'll talk about the third project of the Nanodegree, image classification using AWS SageMaker. First, let's discuss a project brief overview.
We start our project by opening a SageMaker notebook instance. Then we clone the project starter code from GitHub. The project starter code is a train and deploy IPYNMB Jupyter notebook and two Python training scripts, trainModel.py and HPO.py. The Jupyter notebook is the model submission scripts, while the trainModel.py and HPO.py are the model training scripts. We start by downloading the dataset to an S3 bucket. The dataset consists of dog breed images, which is separated into training and validation and testing subdirectories. Each subdirectory contains 133 breeds of dogs. We first start by launching our Hyperparameter Tuning job to find the best hyperparameters for the training model. We define a range of hyperparameter space to search for. Then the Hyperparameter Tuning jobs return the best hyperparameters found during the training. Then, using the best hyperparameters obtained, we launch our final training job with the debugger and profiler hooks attached to it. After we train our model using the final training job, we deploy the model to an endpoint and test the model using test images from the S3 bucket.
So this is our project starter page. First, to start our project, we open an Amazon SageMaker notebook instance. We open Amazon SageMaker page. On the left-hand side, we scroll down to notebook. Then we open notebook instance. We start our notebook instance, and then we open a JupyterLab server. First, we have to clone our starter code repository. This is the starter code repository of our project. We copy the starter code URL. Here we go to Git. We click clone a Git repository, and we paste the URL of the GitHub repository, and we clone the starter code to our JupyterLab instance. In our starter code directory, we see that we have train and deploy Jupyter notebook. We have two model training scripts, train and model.py and HPO.py. They are basically the same scripts, but and we will use these scripts. We will develop them using the same code, but with the minor modifications, minor differences. We start by opening the Jupyter notebook, train and deploy.ipynb. In our notebook, we first start installing the necessary libraries to our project, like SageMaker Debugger. Then we import any libraries and packages that we may need in our project. Here we import SageMaker and Boto3, and then you include any libraries that you may need in your project. Then we define the global variables that our project needs, such as the bucket that we used, S3 bucket, and the role, and any other global variables. In this cell, we download and unzip the dog images dataset. Of course, you can use any dataset of your choice for this project. Now, our dog images dataset is downloaded to this directory. If we open this directory, you will find that our dataset is further divided into training, validation, and testing subsets. If we open any of these subsets, they are basically the same. Each one of these is further divided into 133 subdirectories corresponding to our dog breed images. This is a sample of our dog breed images. This is the first class here in our dataset. If we further examine our subsets, training, validation, and test subsets, using the terminal, we count the number of files in each of these subsets. In our training dataset, we have 6,682 images. In our validation subset, we have 835 images. And in our test subset, we have 862 images. Next, we upload our dataset to S3 bucket to be used by our machine learning algorithm. Let's examine the S3 bucket. The S3 bucket should contain the same subdirectories that we have downloaded here in our local machine. Next, we define our data channels to be used by our machine learning algorithms like this dictionary with 3 keys: train, valid, and test keys. We associate each one of these keys with the bucket, with the subdirectory inside the S3 bucket of the training data. Next, we complete our model training and hyperparameter tuning scripts. They are basically the same script with minor differences. To complete these scripts, you can use helper code from the Udacity classroom. Here in Common Model Architecture and Fine-Tuning module, exercise 13, fine-tuning the CNN model, you will open a Jupyter workspace. It has some code, helper code for your problem. You will train a ResNet 18 or ResNet 50 network to train and fine-tune it to use it as a classifier for dog breeds. Here you can also find a solution code for this module. It has a good helper script to start. You can use it as a start to build your model. You can also learn more about, say, a script mode in SageMaker inside this deploy and deep learning models on SageMaker. Exercise 6, script mode in SageMaker. You can use also the code inside this zip file. The basic difference between model training and hyperparameter tuning script is that in model training first, in model and hyperparameter tuning, you don't have to train the full data set. Okay, there's a trick to stop at proportion of the data set here inside this fine-tuning code. You can see here you can, for example, use 20% of the data set to train the model instead of the full data set to speed up the fine-tuning, the hyperparameter tuning step. You can also inside another difference between model training and hyperparameter tuning is that in model training, you add here debug hooks and profiling hooks. Okay. Another difference is that in model training, you run, for example, a large number of epochs, for example, 20 epochs or something. But in hyperparameter tuning, you only need maximum 2 epochs to train your model. To pass your data channels to your model training scripts, inside the train and deploy Jupyter notebook, you define these data channels as a dictionary like this. Then when you call your estimator, you call estimator.fit and pass the data channels dictionary to as a first argument to this function. Inside your model training script, you can access these data channels and from the environment variables using os.environ dictionary, and you access each of one data channel as an environment variable. For example, training is passed as sm_channel_train, and etc. You can pass your hyperparameters to the model training script as a dictionary of key value pairs. This dictionary of key value pairs is translated as a command line arguments like this to the model training scripts. Inside your model training script, you parse this argument using the argument parser object by calling parser.addArgument methods. Next, I'll talk about the model training and hyperparameter tuning scripts functions. We will discuss them one by one. First, we complete our create data loaders function. This function takes an input channel as data and a batch size. Our input channel can be accessed through the operating system environment variable like this, and can pass as a local directory of input channel. It can has this sample format. This function takes data from the 3 input channels, transforms the data to a size similar to the input of the fine-tuned network, and then returns a data loader object to the main function. First, you create a transformation that transforms the image to the required size. You can also add your own transformations of random mutation to the image. Then you define a torch vision datasets image folder object, which takes the root data of each one of these channels and defines a transformation. Then you create a data loader object that takes this data and returns a data loader object. Next, you define a net function. This function returns a pre-trained model to the main function. Remember that your output should be 133 corresponding to your .p images, and you can use the classroom exercise of fine-tuning this create model function with some modifications. In train and test functions, you will do the main training loop and testing loop of your dataset, of your model. You can do some modifications on this function to take here validation loader, and it can also take device which is a GPU or CPU, and the arguments object, and it can take a debugger on and profiler hooks. And you can also do this for the testing function. Remember, inside your testing function, you should output metrics that indicate the accuracy of and loss of your function. This will be used later by the Hyperparameter Tuner to optimize on your model training script. Then finally, you complete your main model function. In your main model function, you create your model, create a debugger hook. You obtain a reference to the device you'll use, whether it is a CPU or a GPU. You create your loss criterion and optimizer. You associate the debugger hook with the model parameters and losses. You train and test your model. And finally, you save the model state dictionary. To register your loss using the debugger hook, you just add the statement hooker.register loss and the loss criterion to output the loss tensors to the debugger. Finally, to prepare your model for deployment, you should include a model function. This model function takes a model directory and it loads the model. This model function first creates an object of the net function, the pre-trained model, and then loads the state dictionary from the model saved inside this model directory and returns the model to the endpoint model server. You can create this function using from the classroom exercise. You can see help inside this deploy deep learning and models on SageMaker, exercise 12 deployment. When you scroll down, you will find a zip code of the model deployment where you can see an example of this model function. You can test your model training script locally first before deploying it to a training job instance. You can open a Jupyter notebook and import everything from this script inside this Jupyter notebook using this statement from train model import star. And then you can simulate passing environment variables using the sys.argv object. And you can simulate environment variables using these statements. And you can simulate, you can simulate creating a model here inside this model of directory. Of course, you need to import OS and import SYS first. Next, we go to the hyperparameter tuning step by opening the hyperparameter tuning section inside train and deploy notebook. First, you define the search space for your hyperparameters here. For example, you can do hyperparameter optimization on batch size and learning rate. The metric definitions should match the string output from the test function here. Inside this test function should match the output from this test function read from the logs. So inside the model training script, if you choose the zero accuracy, you maximize it. If you choose loss, you minimize the metric. This is an example match string for the output defined before. You should include a regular expression that matches the same output from the test function. Of course, you can test the correctness of your hyperparameter tuning script first before launching a hyperparameter tuning job. You can do this by launching a single estimator by calling estimator here .fit a method, and you pass the data channels. It's better to do hyperparameter tuning jobs in series, not in parallel, to obtain the best results. After launching a hyperparameter tuning job, you can see it inside SageMaker. Scroll to the left-hand side, and it's underneath the training section, you open the hyperparameter tuning jobs, where you can find the hyperparameter tuning job that you have launched. After your hyperparameter tuning job completes, you should take a screenshot of this hyperparameter tuning job and include it with the project submission. Here you will find the best hyperparameter tuning job and the best objective metric that you have obtained. After your hyperparameter tuning job completes, you obtain the best hyperparameter tuning metrics obtained in the previous step. You write them down for the next step to train your final model. For this hyperparameter tuning step, you can refer to the Udacity classroom module underneath Deploy Deep Learning Models on SageMaker, Exercise 11, Hyperparameter Tuning in SageMaker, where you can scroll down this page and open a zip file that contains a helper code for this process. Now let's move to the next section of the notebook, Model Profiling and Debugging. Here you create your final model estimator using the trainModel.py script. And in this step, you add your debugger and profiler rules and configurations. You can see a full example that combines both profiler and debugger in this classroom exercise in module Deploy Deep Learning Models on SageMaker. Number 10, lesson 10, exercise debugger and profiler, where you can open this Jupyter notebook and accompanying scripts and examine them on how to define your profiler and debugger rules. To obtain the loss tensor of your debugger, you need to register it inside this model main function. You register your loss tensor as we have described before. And here inside your debugger config, you define the debugger hook config, passing the S3 output location of your debugger tensors, and you define a collection configuration. This is a list of collection configs. You need to define your output tensor cross entropy loss output. It's important to include a regular expression to match this tensor, like this cross entropy loss output dot star, and then you define your train save intervals and evaluation save intervals and predict save intervals, where the numbers of intervals correspond to the number of training batches. as the training data set is 8 times the validation and testing data set, you can set the training interval to be 8 times the evaluation and prediction intervals. Each interval of these correspond to a batch of each step, each interval correspond to a number of batches of your data set. For example, if you define an interval to be 4 and your batch size is 32, you save this interval after 128 images. Okay. In your training and testing validation and testing loop, you can set the collection mode. For example, here inside your training, you set the mode by passing hook set mode smd modes dot train, and also inside the validation loop, you can pass it using the eval key. Inside the testing loop here, you pass you set the mode using using key predict. Okay, then you run your final model estimator by fitting it to your data channels, as we have seen before. You will see the output from the CloudWatch logs inside your Jupyter notebook. Here we can see that our channels are passed to the model as these directories inside the compute instance training job machine. Inside the test channel, the validation and training channels, we can also see our hyperparameters passed to this compute instance. We can also see here the hyperparameters. Of course, we can access these in the environment variables here inside this machine. We can use these logs to debug our training job process. Then after our training job finishes, we retrieve the output tensors here. The tensor that we are most interested in is the loss tensor, which is here cross entropy loss output tensor. Okay. Then finally, you plot the results obtained from the loss tensor using matplotlib library. Before that, you first retrieve it from the output S3 bucket. If my tensor retrieval run correctly, I should see the length of this tensor is more than 1. Finally, you display the profiler output as an HTML inside your Jupyter notebook. Remember to include the profiler output HTML in your project submission. This is how it should look. Finally, we move to the final section of our notebook, model deploying, where you deploy your trained model to an endpoint and test the predictions output from this endpoint. For a reference, you can use to implement this section, refer to this classroom example. This is underneath the deploy deep learning models in SageMaker, lesson 12, deployment, where you can scroll down here and download this zip file for helper code. So first, make sure you have correctly implemented the model function inside your train model script, as we have discussed before. So first, you start by loading test images from your local directory. You load your test images from the local directory as NumPy array of batches of images. First, you import your data loader function that you have created before from the training script. This data loader function is what you will use to load test images from the file system. Then you use the data loader to load test images from inside the this directory on your file system. You can use it to test images like this. After you load it, you load the test images. You can load your images either in batches of 4, or you can load it as single images by making the batch size 1. Make sure not to increase the batch size above 10, or your predictions won't, your endpoint won't respond. This is how you load a batch of test images. And your test images should be 4-dimensional like this. For example, this the shape of your tensor that you should pass to your endpoint should be like this. For this, the first number is the batch size. The second number is the number of channels. The third and fourth number are the width and height of the image. The image array is passed to the predictor, and then you retrieve the predictions as an array of predictions, and your notebook should demonstrate the result output from the endpoint as predictions. And it is helpful to plot the test images to check if the predictions match the ground truth or not. Finally, before you delete your endpoint, you take a screenshot of your deployed endpoint and save it to be submitted with your project. And remember to finally delete your endpoint after you finish in order not to consume too much resources. This is the conclusion of Project 3 walkthrough. Thank you for watching and wishing you good luck in completing and submitting this project.